This is an application problem where we're going to need to use the chain rule on a function with several variables. The temperature at a point xy is T temperature that depends on xy, measured in degrees Celsius. A bug crawls so that its position after t seconds is given by these two parametric equations, where x and y are measured in centimeters. The temperature satisfies these two given partial derivatives, and the question is, how fast is the temperature rising on the bug's path after 3 seconds? So in order to understand this given information, I'm going to make a concept drawing to try to decipher it. So let's say this is our surface function. Again, we are not given the surface function, but we are given some information about its partial derivatives. So when we're at the domain element 2, 3, somewhere around here in the floor, we get an output on this temperature function, but we're not even actually given what that temperature output is. So for right now, let's just call it the temperature evaluated when the bug is at the ordered pair 2, 3 in the domain. Now let's recall what the first partial of t with respect to x actually means. It means we slice the surface with a constant y-plane, and if we're looking at the ordered pair 2, 3, it means that the y-plane that we're slicing with is the y is equal to 3 plane. So if we slice this surface with a constant plane y is equal to 3, we'll get a tangent line to the surface at this point, and the slope of this tangent line would be 4. So what this means is that the output temperature is going up by 4 degrees Celsius for every 1 centimeter in the direction of an increase in x. So if our bug travels 1 centimeter this direction, the temperature is going to increase by 4 degrees Celsius. Now similarly, if we were to look at the first partial of temperature with respect to y at this ordered pair 2, 3, we were given that this value is 3. What that means, if we were to slice this surface with a constant x-plane, and specifically that would be the constant plane x is equal to 2 because of the position of our domain element. So here is our constant x is equal to 2 plane, slicing into the surface and giving us a line that is tangent to the intersection curve at this ordered triple. And the slope of this tangent line is equal to 3, which can be thought of as 3 over 1, or the change in the temperature with respect to a change in the direction of y, which is the only thing that's changing because x is being held constant, meaning that if my bug were to travel this direction 1 centimeter, the temperature would go up by 3 degrees. Now, my temperature concept drawing appears to be going down, so this is not a great drawing. The slope of this line should actually be up 3 degrees Celsius for 1 centimeter change in the direction of y. So I should have a tangent line looking more like this, but my concept drawing is just to give us an idea. So the question is, how fast is the temperature rising on the bug's path after 3 seconds? Another way of thinking about this question is to ask for the instantaneous rate of change in the temperature at 3 seconds. But before we can specifically talk about that rate of change after 3 seconds, we need to first find the rate of change in temperature, let's say with respect to time. And when we see the phrase instantaneous rate of change, what that says is that we're looking for the derivative of the t function with respect to the parameter. Now the question is that going to be a partial or is that going to be a straight d derivative? Well, let's come back up here to the top. We see that cap t is a function of x and y, temperature, but x depends on time in seconds and y also depends on time in seconds. So let's build our custom chain rule tree diagram, and we see that cap t depends on both x and y, but x depends only on t and y depends only on t. So ultimately, t temperature depends only on t time. There's only one variable down here in the root system, so we're actually calculating a straight d derivative. And our custom chain rule tree says that we need to first get partial t respect x, multiply that by dx, this is a straight d, x dt, because x depends only on t, plus going down the y branch, we're going to have partial t respect y, times from y to t, that's a straight d derivative. And this is the formula that we're going to need to use in order to calculate the instantaneous rate of change in temperature with respect to time. The partial of temperature with respect to x was actually given in the original information. So was the partial of the temperature with respect to y. But we'll need to calculate dx dt and we'll need to calculate dy dt. So let's bring down these two first partials from the given information. And also, as a reminder, the x parametric equation, the x function that depends on t, was 1 plus t, and the y function that depended on t was 2 plus 1/3 t. So dx dt can also be written as x prime t is going to be 1 over 2 radicals 1 plus t. dy dt can also be written as y prime t is the derivative of our y parametric equation, which is just going to be 1/3. Now we're asked about the temperature change at time is equal to 3 seconds, so we're going to plug in t is equal to 3 to both of these derivatives. So we'll say x prime evaluated at 3 is 1 over 2 square roots 1 plus 3, and this is going to be 2 times square root 4, which is 2, so 2 times 2 is 1/4. And since y prime is the constant 1/3, that's not going to change when we plug in t is equal to 3. So this entire formula can actually be rewritten using prime notation and subscript notation as the first partial with respect to x at a given domain element times x prime at t plus first partial with respect to y at a given domain element times y prime at t. Again, we're looking at time is equal to 3, and by the way, the position at time is equal to 3 is going to be, after we plug in 3 for t, the square root of 4, which is actually 2, and plug in 3 for the y position parameter, and we get 1/3 times 3 is 1 plus 2 is 3. So our position at this time is 2, 3, which is a good thing because we've based all of our stuff off of that domain element. So when we're looking at t prime at 3, we are looking at the partial derivative with respect to x at the position 2, 3 times the first derivative of our x equation evaluated at 3, partial y evaluated at 2, 3 times y prime evaluated at 3. So again, this was given to be 4 times x prime evaluated at 3 was 1/4 plus partial derivative with respect to y at 2, 3, that was also given to be 3 times y prime evaluated at 3 was 1/3. And then when we multiply all of this together, we get 4 times a fourth is 1, 3 times a third is also 1, so we get 2. Now, what are the units here? Remember, d prime is basically the same thing as dt like this. So when this value turns out to be 2, we can drop a 1 under it and think essentially about the units of the temperature that are in the top here. Temperature is measured in degrees Celsius, and the unit of time that's in the bottom here, time is measured in seconds. The instantaneous rate of change in the temperature after 3 seconds is that the temperature is increasing by 2 degrees Celsius per second.